All right, we now have the first of our shorter talks this afternoon. The first one being given by Francesca Pratali.
Thank you. Okay. Oh, okay, so hi to everyone. So first of all, thanks to the organizers for this very nice conference so far and for this opportunity. And today I'm going to talk to you about these straightening and straightening equivalence for infinity operads, and more generally about the notion of Lefebvreation of infinity operads that I'm going to call operatic Lefebvreation. And in order to start, let me give you some motivation. And so let me start with the usual, like classical straightening and straightening theorem for infinity categories. So this heavily relies on the notion of Lefebvreation of infinity categories. So this is a disclaimer. I'm going to like to use the language of infinity categories, and but later on, feel free to like ask me more details if this is not clear. In any case, so given an infinity category C, one can define the infinity category of Lefebvreations over C, and these basically what are Lefebvreations over C? These are infinity categories over C, which are co-fibered over C. What does it mean? Well, it means basically that for any object of C, well, we have a fiber, and this fiber is a space in the case of Lefebvreation, so a topological space up to we come out of equivalence. And the property of being co-fibered means that whenever we have a morphism in C from an object C to another object D, there will be an induced map between the fibers. So from the fiber over C to the fiber over D. Okay, and well, then the straightening and unstraightening theorem, which is originally due to Grothendieck, but then to Lurie in its model formulation, states that whenever we have an infinity category C, and I'm going to denote, I'm very sorry, by S, the infinity category of spaces. So let me just. Okay. Straightening and straightening theorem says that, well, the infinity category of Lefebvreations over C is actually equivalent to that of covariant functors from C into spaces. And moreover, this equivalence enjoys this very important property that whenever we have such a covariant functor, the fiber of its unstraightening over an object C of C will be equivalent to the value of the functor on C, and this equivalence is natural in C, which means that whenever we have one morphism from C to D, the induced map between the fibers is actually equivalent to the map that we have from FC to FD, given by the fact that F is a functor. Okay, so what we want is an operatic generalization of this statement. So we are interested in replacing an infinity category C with an infinity operad P. Here, infinity means, infinity operad means an operad weakly enriched in topological spaces. And so what we're interested is in considering not only one morphism, so not only morphisms from one object to the other, but multimorphisms from several objects to another. Okay, so under this generalization, space-valued functors over an infinity category C become space-valued algebras over an infinity operad P, and then the notion of infinity category co-fibered over C needs to become some multiplicative version, which we are going to call operatic Lefebvreation. So we need to be able to formulate the notion of infinity operad co-fibered over P. So what does it mean that it has to be a multiplicative version of being co-fibered? That, well, whenever we have an operation in P, so in the base infinity operad, there will be an induced map between the fibers, but this time between the product of the fibers of Q over the input objects to the fiber over the output object. Okay, and then under this generalization, an operatic straightening and straightening equivalence should establish an equivalence between, well, the infinity category of operatic Lefebvreations over an infinity operad and that of space-valued algebras over the infinity operad. Great. So this is quite vague for the moment, and so let's be a bit more concrete. Now, concretely, there are actually several different but equivalent models for infinity operads, and well, although these models are equivalent, the definitions of algebra and of operatic Lefebvre are performed inside each model. Inside each model, using features which are using feature proper of each model. So a priori, they are not equivalent. So it is natural to ask for, well, first of all, operatic straightening and straightening equivalences in each of the models for infinity operads, because one may want to use one model over the other for practical purposes, but also the model invariance of the notion of algebra and of the notion of Lefebvre of infinity operad, so that we're sure that whenever we switch from one model to the other, we're actually considering the same infinity categories. Okay, now in this talk, I'm going to focus on two specific models. So Lurie's model for infinity operads, the one we find in higher algebra, and then the dendroidal model for infinity operads given by complete dendroidal Siegel spaces, first due to Szyszynski and Mordalik. Now, sorry if I just wrote the initials, but there were a lot of names, but combining the words of Heutz, Hinich, Mordalik, Barwick, Chu, Hausen, and Heutz, we know that these two infinity categories are equivalent. So complete dendroidal Siegel spaces and Lurie's infinity operads are indeed equivalent. But what about the algebras? What about the operatic Lefebvre? What about the straightening theorems? So what we have so far is the following. Both models enjoy operatic straightening and straightening equivalences. So for complete dendroidal Siegel spaces, this was proven by Guavida-Mordalik, which made sense of a notion of operatic Lefebvre in the dendroidal context, which they called dendroidal Lefebvre, and which made sense of the notion of algebra over dendroidal infinity operad, and then proved that there is an equivalence between these two infinity categories. And also in Lurie's model, we do have a straightening and straightening theorem, which is due to Ramsey, which basically makes use of the notion of operatic Lefebvre and of algebra over an infinity operad that we already find in higher algebra. What about the model invariance of these infinity categories? Well, there is not much about operatic Lefebvre, to my knowledge at least, and we do have some partial comparison results for algebras over infinity operads. In the case P is actually a simplicial operad, so an operad enriched in simplicial sets, and these are due to Pavlov and Stolberg. So in this talk, I'm going to present to you some stuff, and the first one is another straightening and straightening theorem for infinity operads in Lurie's model, which makes use of the symmetric monoidal envelope. So basically, which allows to reduce the straightening and straightening equivalences for infinity operads to questions about symmetric monoidal infinity categories, which is sometimes easier which are sometimes easier to manipulate. Then I will also prove that there is actually an equivalence between dendroidal Lefebvre over a dendroidal infinity operad and operatic Lefebvre over a Lurie infinity operad. And in particular, combining these results, we obtain also a general model invariance for the notion of algebra over an infinity operad. So we will be able to prove that algebras over a dendroidal infinity operads, they define the same infinity category as algebras over a Lurie infinity operad. Okay, so let's start. And let me start with the first results. So with the straightening and straightening theorem for Lurie's infinity operad. So let me start with by introducing the symmetric monoidal envelope. So I will denote. No, well, I wanted to point it, but whatever. So SM cut infinity denotes the infinity category of symmetric monoidal infinity categories with strong symmetric monoidal functors. Every symmetric monoidal infinity category is, in particular, an infinity operad. Okay, it's just the operations are representables. And this symmetric monoidal envelope, first defined by Lurie in the infinity categorical context, is a functor from Lurie's infinity operad to symmetric monoidal infinity categories, which is left adjoint to the forgetful functor that we have from symmetric monoidal infinity categories to infinity operads. We can rephrase this in a maybe more useful way by stating its universal property. So the symmetric monoidal envelope has the universal property that for any infinity operad O and for any symmetric monoidal infinity category V, the infinity category of O algebras in V is equivalent to the infinity category of strong monodal functors from the envelope of O into V. Okay, so first of all, we have, and we're going to use this description of the infinity category of algebras over an infinity category. Okay, we make this very important observation whenever the symmetric monodal infinity category we are considering is Cartesian, which means that the tensor product is just the Cartesian product, then we can actually identify the infinity category of strong monodal functors from the envelope into V, or from any other symmetric monodal infinity category, as a full subcategory of functors from the infinity category of operators of the envelope into V. And this is quite important because a priori on this hand side we have a structure, and here we just have property. So it's an important identification. And Kimmich first observed that if we consider a symmetric monodal infinity category C, then the straightening and straightening equivalence for its infinity category of operators, so we're not considering the underlying infinity category, but the whole structure, actually restricts to an equivalence between lax monodal functors from C into spaces and an infinity category that it calls an infinity category of symmetric monodal aberrations. Basically, this is a full sub-infinity category of symmetric monodal categories over C, where the objects are morphisms of symmetric monodal categories, which are also left fibrations once we forget that they were symmetric monodal. Okay, so the first thing that we prove is that this result can be upgraded, and in order to obtain a characterization of the unstraightening of strong monodal functors out of symmetric monodal category.
So can I ask just on this left vibration, you mean left vibration on the operator category, not on the underlying?
No, exactly, yeah, on the operator category, yes. This is important, and this is because basically we are restricting the equivalence basing on this inclusion. Okay, so our first result is that whenever we have a symmetric monodal category, then the straightening and straightening equivalence for the infinity category of operators restricts to an equivalence between strong monodal functors and strong symmetric monodal aberrations, namely those aberrations which satisfy these properties, this property on the fiber. If you remember the correspondence between fibers and value of a functor on an object, this is straightforward. I mean, it's very credible, at least. Okay, so this is our first step. Let me now introduce the notion of operatic left vibration. So inspired by basically the Kimmich work, we give the following notion of operatic left vibration. So we say that a map of infinity operads is an operatic left vibration if it is a left vibration once we forget it was a map of infinity operads. Okay. How can we check that this is indeed the correct notion? Well, it turns out that with this definition, whenever we have an operatic left vibration over O and a multimorphism from C1, Cn into D of O, there is actually an induced map of fibers from the product of the fibers of the total operad over the input objects to the fiber of the total operad over the output object. This is the notion of being multiplicatively cofiber that we were looking for at the beginning. So great. And we define left operad as the infinity category of operatic left vibrations. Okay, so let's put all together. And well, the first element that we prove is that for every infinity operad O, the symmetric monodal envelope sliced over O establishes an equivalence between operatic left vibrations over O on the one hand and strong symmetric monodal left vibrations over the envelope of O. Perfect. Then we can pack all together and see that by instantiating the symmetric monodal infinity category of the previous proposition with the envelope of our infinity operad, we obtain an equivalence between operatic left vibrations over O and O algebras in spaces. And moreover, this equivalence actually respects the correspondence between fiber and value of an algebra on an object. Okay, so Yeah, so this is the first point we wanted to, I wanted to present to you. So another straightening and straightening equivalence for Lurie infinity operator. Okay. Now, what about operatic left vibrations? So what about these other dendroidal model that we want to consider? And okay, so I assumed that you were familiar with Lurie's infinity operads, but I will not assume that you're familiar with the dendroidal model. So let me just briefly introduce this to you. So the dendroidal model, here I'm going to talk about complete dendroidal single spaces. So basically relies on the intuition that an operation with an operation with several inputs and one output can be depicted as a tree with n input edges and one output edge, which is the root. Okay, so this is the intuition behind the dendroidal formalism, basically, and that the operatic composition of multimorphisms actually corresponds to grafting trees of one on top of the other. Okay, concretely, how is this accomplished? So Mordek and Weiss defined the dendroidal category omega, whose objects are finite, non-rooted, non-planar rooted trees. So I draw some examples. And where the morphisms, well, the morphisms can be defined in several ways. But for instance, we can realize omega as a full subcategory of discrete operads by observing that any tree, any non-planar finite rooted tree, defines a free discrete operad. Whose so in particular, let's take this example. Very simple example. So we have this tree with one vertex and three input edge and one root. So the operad, the discrete operad it generates, it will have as objects the edges of my tree. And then the operations will be freely generated by the vertices. So in this case, it's easy because we only have one operation. Okay. And then what just says, yeah, maybe I should have written this, but then what just says that morphisms in omega from a tree S to another tree T are just morphisms of discrete operads between the operads generated by these trees. This definition is actually analogous to the one we can give for the simplex category delta, as any poset determines in particular a category. And indeed, delta, so the simplex category embeds into omega. So we can realize any poset, any totally ordered set of n elements as a linear tree. So it's kind of, and yeah, we can realize it as a linear tree, and actually this embedding fits into a commutative diagram of this type. Okay. Great. So this being said, we can give the definition of dendroidal infinity operad, and we define a dendroidal infinity operad as a presheaf on the dendroidal category omega, such that, well, a dendroidal Siegel condition holds. So what does this mean? For any tree T, which is obtained as the grafting of two smaller subtrees, we want that the natural map from the value of x on the big tree to the fiber product of the values of x on the smaller subtrees is a weak homotopy equivalence of spaces. This basically means that the value of x on a composed tree is just determined up to homotopy by the values on the single corollars. And then, okay, this is another technical condition, but we ask that the restriction of x to the simplex category determines a complete single space. Great. Okay, now we define dendroidal infinity operads as the full subinfinity category of presheafs over omega spanned by the complete dendroidal single spaces. Okay. Okay, so this is a bit, you will have to trust me a bit, I think, because it's hard to explain this in 5 minutes. But, okay, but we can, okay, so in this formalism, how can we make sense of the notion of left vibration of infinity operads? we can do so by generalizing the left Horn inclusions that we have for simplices, that are the ones defining the notion of left fibration, to leaf Horn inclusions of trees. So I will just do an example instead of giving the whole definition. But for instance, if we take, well, I actually draw it. So if we take a 3T given by a corolla, then its leaf Horn inclusion is just given by the disjoint union of the input vertices. And then we say that, okay, so this is it. And then we say that a map between dendroidal infinity operads is a dendroidal left fibration if it is local with respect to these Horn inclusions. Concretely, if we take the Horn inclusion given by the example that you see, this means being local with respect to this inclusion means precisely that every diagram of this form admits a lift. What does this mean again? It means that, well, a map from the corolla into X will select precisely a multimorphism of X. A map from the disjoint union of trivial trees into Y will just select N objects of Y. And having a lift of this diagram means that whenever we choose a multimorphism on the base infinity operad and lifts of the input elements, we can actually find a lift of the whole multimorphism, which then projects back into the operation I started with. Okay. And we define dendroidal left fibrations as the full subinfinity category of dendroidal infinity operads over X. Then it is a result, as I was mentioning before, of Boisvide-Mordyke, that dendroidal left fibrations are equivalent as an infinity category to algebras over space-valued algebras over a dendroidal infinity operad. Here I'm adding something under the carpet because what is this? What are algebras over a dendroidal infinity operads? Well, actually, they are defined as simplicial algebras over the Borman-Vogt resolution of our dendroidal infinity operads. So we have a dendroidal infinity operad, we associate a simplicial operad, we take algebras, simplicial algebras over these simplicial operads, we put the projective model structure, we take the infinity category associated. That's okay. So you see, it's desirable to know that all these things are equivalent so that one can really safely switch between the models. And well, in order to prove that actually dendroidal left fibrations and operatic left fibrations in the Riesz model are indeed equivalent, we take as a starting point a direct equivalence between dendroidal infinity operads and Rie infinity operads established by Hinich and Mordyke, based on a functor that we already find in works of Hoyts, Hinich, and Mordyke, which goes as follows. So recall that dendroidal infinity operads we said are a full subinfinity category of presheaves over omega, while Lurie infinity operads can be identified as a non-full subinfinity category of presheaves on the category of simplices of the nerve of the category of finite quantity cells. Okay, great. Then what all these people do is that they build a functor from the category of elements of phi into the completion of omega under finite products. But the point is that basically omega really translates the intuition of what is what is operatic. Okay, well, in any case, omega just omega is able to associate to any string of composable morphisms in phi a disjoint union of trees, and this basically translates the intuition that there is behind the Riesz model of infinity operad and the dendroidal model of infinity operad with respect to parametrizing operations in an operad. Okay. In any case, there is this functor. I'd be happy to tell more if you want. This functor induces a map between the category of presheaves, and what they prove is that omega star restricts to an equivalence of infinity categories between dendroidal infinity operads and Rie infinity operads. What I prove is that if we take a dendroidal infinity operad X and its Lurie equivalent infinity operad, then this equivalence induces an equivalence between dendroidal left vibrations over X and operatic left vibrations over the Lurie equivalent to X. If we combine all these results together, we also find an equivalence between the infinity category of algebras over a Lurie and a dendroidal infinity operad. And I am finished. Thank you.
We also have this notion of the generalized infinity operads.
Right.
Do you know if these operatic left vibrations also extend to that setting and whether there's some kind of straightening or straightening?
I do not know, but I know that there are several straightening theorems. But no, I do not know. I do not know about generalized infinity operads. This is the truth. I know that there are, for example, straightening theorems for Siegel objects for algebraic patterns, for instance. But I don't know if this falls in the case you asked. Yes.
There's no further questions. We have a very quick turnaround, so our next talk will be at 3:30. Let's thank Francesca.